quantum computing by myself, Beachwood Computer Security Club. I wanted to start with going over like the current CPU design, sort of how we do it now. And so basically you take a silicon wafer. This is 99.99999% pure silicon. You engrave a bunch of basically MOSFET transistors onto this. And by doing this, you can construct logic gates. And by chaining together these logic gates, you can get larger sets of instructions. And so all a computer program does really is just give different voltages to these logic gates. And by doing that, the CPU can execute its instruction set. And that's how we get our computer programs. So the most important thing with CPUs, or one of the most important things with CPUs, is the transistors. Transistors are basically switches. If you think of like a light switch, it's a physical switch and it controls an entire current. Same thing with a transistor. If you put a small voltage at the base of a transistor, it allows current to flow across the transistor. So more transistors is better, and there's a few reasons why this is. If you have a smaller transistor, it takes sort of less time to react, because transistors, every electronic component has like a small capacitance, and transistors also have a capacitance. And so if you have a higher capacitance, a bigger transistor, it'll take longer to charge, and so it'll take sort of longer to react. So you have a smaller transistor, you have a smaller capacitance, and it'll be a quicker reaction time. If you have small transistors, they'll be like closer together. You can pack them closer together, and so the signal time from one end of the CPU to the other end of the CPU is better. And like, so the speed of light is 300 million meters per second. If you're talking about like the nanosecond timescale, that actually becomes kind of relevant, because light can only travel around 10 centimeters in a nanosecond. So if you think about like a large chip, you might actually have problems with getting different parts of the chip synced together over one clock cycle, because you're talking about like gigahertz in terms of your frequency. The other thing with transistors is, if you think of sort of your worker, right? A worker in a workshop, he's got the sort of hierarchy of storage. He has his tool belt, which is like the tools that he can immediately access, the parts he can immediately access. He has his workbench, which is like quick access, but not as quick as his tool belt. He has his tool cabinet, which is the largest, but it's the slowest to access. So if you sort of go by that analogy, your CPU cache is like your tool belt, your RAM is like your workbench, and your hard drive is like your tool cabinet. So if you have a larger tool belt, which is a larger CPU cache, then you can work more quickly. You can store more things into that tool belt, and it's going to be easier to do like calculations with that tool belt. And so if you have more transistors, you can get a larger CPU cache. And lastly, if you have more transistors, you can do like more parallelization. So you can break up tasks into several smaller tasks, and you can do these subtasks in sort of like massive parallelization. This is essentially what a GPU does. So yeah, these are the advantages of having a higher transistor count, but there's a few reasons why this is problematic. So as you pack your transistors tighter together, it becomes very difficult to dissipate the heat. Because if you think about it, you have like electrons flowing, right? There's obviously going to be some resistance there. And so with the resistance due to ohmic heating, you will have these transistors heat up. And your CPU temps, you don't want to be able to cook an egg on a CPU. So you have to be able to dissipate that heat somehow. And as you pack them tight together, it becomes increasingly difficult to get that heat removed. Our current manufacturing technologies also are sort of limited, because currently transistors, their sizes are in the nanometer range. So the way we currently engrave our silicon wafers to engrave the CPUs is we use like basically, I think it's UV light and some sort of like filters. And this sort of creates an etching pattern. But it gets more and more difficult to make those filters to get the etching pattern as you go smaller. And when you're in the nanometer scale, as we are with our current transistor technology, it's like At a certain point, you can't get smaller. We're talking about like atomic scale here. So it's very difficult to get something smaller than like a few atoms. I mean, just in terms of manipulating the material. And the last point is that at a certain point, the transistor gap is so small that the electrons can quantum tunnel across the junction when they aren't supposed to. And so this is like the sort of another problem we're running into now is quantum tunneling. And when you have electrons flowing when they shouldn't be flowing, that obviously creates problems. You're corrupting data, you're breaking your logic. It's not good. So this is where quantum computing comes in, because at small scales, the universe is very, very weird. So you have objects such as electrons that have properties that are in superposition. So an electron has a quantity called spin. What it is isn't really that important, but spin in an electron can either be like spin up or spin down when you observe it. But when you aren't observing it, then the spin can it's in the superposition of sorts. You can't really describe it as between states. It's more of it occupies every single state at once. And then the act of observation, the act of measuring the spin, if you try and force that electron, or if you try and measure that electron and say, okay, what is your spin? You are collapsing that it's a wave function, essentially, of what the spin will end up being, and you force it into spin up or spin down. So the act of measurement destroys this superposition of being in all states at once. So here's a sort of diagram to show that. So in superposition, you have a bit, and it's either on or off. In quantum, it's sort of like here they use like a sphere, and if it's like a vector in a sphere, it's like pointing in all the directions on the sphere simultaneously, and then you force it via the act of observation to converge. So this is useful because if you take a vector of 4 classical bits, right, it can exist in 2 to the 4 or 16 possible states, but it's only in one state at a time. So if you have 0, 0, 1, 0, for example, that's only one state. If you have a vector of 4 qubits, which are all in superposition, then they are in these 16 states simultaneously, right? Because if you have 4 qubits with 4 electrons in superposition, all the qubits are in superposition, and so it could be like 1, 0, 0, 0, it could be 1, 1, 0, 0, etc. But a lot of the popular media sort of stops at this point, and they say, okay, that's how the power is. That's how you get the power. But that's not helpful necessarily, because if you do an operation on this sort of vector of 4 qubits, and then you try and measure the state, you'll get a random outcome. It'll tell you nothing. But you can still use this to get improvements, but you need a very clever algorithm to do it. And so that's where sort of quantum algorithm design comes in. And this is really the crux of quantum computing. So one example of this, and probably the most famous example of this, is factoring a prime number. And this is called Shor's algorithm. This is going to be a bit mathy. So if you lose me, or if I lose you, just holler out and I'll try and go back over. But factoring a prime number is one of the problems that are like NP. So if you're given a large prime number and you have to factor it, it's very difficult to come up with a factorization, right? However, it's very easy to verify that a factorization is correct. You just multiply them back together. Whereas if you have to come up with a factorization, it's very difficult. So this NP problem is something that quantum computing can be very good at. So we know a prime number, by definition, has exactly one factorization. And with prime numbers, there's a very interesting property. So you have this prime number, you know it's prime, we call it n. The sequence x to the k modulo n has a certain period where it repeats. So if you think of like 2 to the k mod n, right? It'd be 2 over 15, 4 over 15, 8 over 15, 16 over 15. And if you plot the remainders of like, if you plot modulo, right, is remainder. So if you're plotting the this operation, it repeats. And so, and from this period, you can basically, the period's a multiple of basically the factors. So basically you can sort of decompose this prime number into a wave with a period, and from the period you can get the factors. This isn't useful for classical computing, because with classical computing you would have to compute the entire sequence. You need to compute this over all values of x. So it'd be another brute force algorithm. But in quantum computing, you can do a superposition of all of the integers. So you could do, instead of trying this with each integer between like 2, 3, 4, 5, you could try this basically with all of the integers, or a lot of integers, not all, but a lot, in superposition. And with that superposition, you can use what's called a quantum Fourier transform to identify the period. Now, I'm not going to describe what a quantum Fourier transform is, because it's very, very, very out of the scope of this. But a Fourier transform in the classical form takes a function, right, a wave, and breaks it down into the composite waves. So a Fourier transform would be able to tell you that like the wave sine squared times cosine squared is made up of sine squared and cosine squared. In the same way, a quantum Fourier transform can tell you what this wave, this sort of plot of the sequence, is made of, and then it'll give you P or Q. And this is another speed up. So along with the superposition you have that iterates over all of the numbers that could be factors, the quantum Fourier transform in big O notation is n log n versus n times 2 to the n. So you think about it, in classical terms, this is an exponential operation. As you increase the n you have to search over, it grows exponentially. This is less than exponential, so it's a lot faster than the classical operation. And so we've actually proven that this algorithm is much faster than the classical form of finding prime numbers. And it's been successfully implemented. We factored the number 15 with it, so that's something. The one thing about quantum computing is that you never get an actual 100% verifiable answer. Shor's algorithm, for example, you need to run a few times and see like what outcome comes up the most often, and also since factorization is like an NP problem, you can easily verify the answer and see if it's correct. But basically, a quantum computer will never give you an answer you know for 100% certain is correct. A quantum computer is like a probabilistic engine. And so the trick in quantum computing is to take that superposition of the input states and come out and you output something that you think is correct, that has like a 50% chance of being correct or a 20% chance of being correct. And you can verify that with a classical computer, because a lot of problems are hard to solve but easy to verify. So the algorithms basically are like try and extract what is probably correct from the superpositions. In terms of like the physical implementation of quantum computing, noise is a big one. So if you think about in the world of quantum, a measurement isn't just like a human looking at a bit. If I like shoot a photon at an electron, that's measuring it. Or if a atom collides with an electron, that's measuring it, because it's basically altering the state and it's reacting to the state. So if you have a bunch of qubits, you have to shield them from the outside world somehow. So this involves cooling them to around 20 millikelvin. It involves putting them in like sealed boxes so cosmic rays aren't interacting with them. It involves eliminating stuff like mechanical vibration from the earth. It's insane how you have to treat the qubits. And the other thing with qubits is you can't copy them. Because if you think about the act of copying something, you have to measure something to copy it, right? If I wanted to copy the number 33, I need to look at it and copy it, basically. You can't do that in quantum. So it's very difficult then to devise algorithms. And what we instead have in quantum is these like logic gates that output like an okay copy like it might be a good copy, you don't know. And so because of that, error correction is also difficult. So that's another issue with quantum computing is like you can't copy bits, and because of like the noise and all that and the fact that qubits are constantly getting disrupted, you have to somehow figure out how to correct the errors that will rise. But there are some potential applications. So cryptography, I just went over the prime factorization thing. Solving linear equations is a big one. If you think about something like machine learning, right, you're basically just solving linear equations. And a lot of engineering problems, a lot of physics problems, whatever, boil down to, okay, how do I solve these linear equations? So there was an algorithm devised, the HHL algorithm, and I think it's been proven to be like optimal in terms of being quicker than like our classical methods of solving equations. So that's pretty cool. And simulation of like quantum chemical effects is another thing. That's what actually Richard Feynman proposed, because, for example, a lot of our drugs require on like chemical reactions, and these chemical reactions do have like some interactions with the quantum world. So if we're able to simulate, you can simulate quantum things using a quantum computer. And so if you're able to simulate these quantum chemical reactions, that's billions of dollars in pharmaceutical research costs, and it's overall like pretty good.
So there was this research that like came out yesterday or something.
Yeah.
And these researchers in Australia, and they collaborated with like researchers from Japan and Finland and all over the world, and they made this chip that can operate at like 1.5 Kelvin, which is 15 times warmer than the computing chips they use now.
Yeah, I think I saw something like that. I haven't like looked at the paper, but yeah, they said it's like, because that's, if you think about cooling something like
qubits.
Yeah, because if you think about it, it's like way more difficult to cool something like millikelvin range than just to cool like a Kelvin or two.
Yeah.
So I haven't looked at that, but that's like a really interesting.
It's like only a few $1,000s to cool it down.
Right, few thousand versus millions.
Yeah, versus millions.
So
also, you talked about superposition, but don't they also use quantum entanglement in quantum computing?
Yeah, entanglement is sort of like a consequence of putting things into superposition. If you like, so it's kind of difficult to describe, but like if you entangle a bunch of or if you put a bunch of qubits into superposition and you do calculations with them, they will like logically also get entangled. So I guess we can talk about the current state of quantum computing. So quantum supremacy is a term that's been thrown around, and it's defined as like a quantum computer beating a supercomputer at a problem. So this can be like a quantum computer factoring a number quicker than the supercomputer or whatever. Google claimed to achieve this in October of 2019 on verifying that a sample of a number was random. IBM challenged this. Google stated that that doing this would take like 10,000 years with a supercomputer. IBM claimed it would take like 2 days or something. So this claim of quantum supremacy is currently disputed. But yeah, our maximum qubit count is somewhere around 50 to 75. And currently they lose it's called decoherence, essentially, when noise affects them too much and they collapse into a 1 or a 0. So our current qubits have like a decoherence time of like 100 microseconds. Another interesting thing is D-Wave systems, they've been in the news like frequently since like 2011. They claim to have this 2048 qubit chip, but there's no evidence that quantum effects are actually doing anything there. Their device isn't really a quantum computer in any sense. It's something else called quantum annealing, but it's not comparable to like Google's machine. It's not a real quantum computer essentially. D-Wave is basically just explaining this for the marketing hype and the VC capital. So
the significance of 2048 is that most RSA encryption is 2048 bits, right?
Yeah, but I don't know if the 2048 qubit has anything to do with like the RSA encryption, because they also claim to have like a 5,000 qubit chip in the works.
Oh, okay.
I don't know if it, like I think
Imagine
I
if
don't know where they.
hackers get their
Hmm?
hands on a quantum computer. All the banks will. There would be no such thing as encryption anymore.
Yeah, so this is like, I guess we can move on to discussion. So one of the things I was thinking about was like, what if a government, like the U.S. government or the Chinese government or the Russian government, invests $150 billion, let's say, into creating a quantum computer, right? It's like a Manhattan Project. You get all the smartest people, you get them in like an area, and you have them working on making a viable quantum computer. If that works, and it's like it achieves quantum supremacy in terms of factoring prime numbers, that country automatically becomes the most powerful country on Earth because it now has a computer able to factor ever able to crack every password on Earth, right? So
That's insane.
like I don't know, like it seemed like the U.S. Army, for example, looks at everything. I don't know if they've looked at that, but it's kind of a neat idea. Um, I also there's an interesting parallel to be drawn between quantum computing and nuclear fusion, controlling nuclear fusion, because controlling they both sort of arose in the 50s and 60s as sort of, hey, this is a really attractive prospect. This is something really cool. But we've had difficulties with both. With controlling nuclear fusion, it's about trying to confine this $150 million Kelvin plasma using magnets and preventing it from destabilizing itself in microseconds. And it's a very hard thing to do. It's almost the same thing with quantum computing. You have these things at millikelvin or Kelvin. You have to somehow keep them isolated from the outside world, and you have to keep a sort of coherent state. So I don't know if any of you have like other thoughts about like the hype surrounding quantum computing or like the security or anything. We can do a discussion.
Wait, does everything use RSA encryption? Or like a lot of things use RSA encryption? I didn't know about it.
Karmanyaah is probably more qualified.
Most
Yeah.
corporate VPNs do, so all company secrets.
So you said it doesn't have anything to do with quantum computing?
What doesn't?
The 2048 number?
I don't think it does.
That's really cool stuff.
I mean,
I think the military has moved on to like 3,000 something bit encryption, but it's just at this point, like if someone can crack 2,000, they can crack 3,000.
yeah, because it's like it's hard to exaggerate how like much of a speed up the quantum factoring algorithms are versus classical factoring. Like it's like this is a big difference when you have a big O notation of 2n versus n log n. So yeah, a successful quantum computer would be able to crack like 16,000 bit encryption. I mean, if you really want to go that far.
How would they control the logic gates?
So
computers? Is that
like how the logic gates like physically work?
Yeah.
It's like not like a clear thing with this. It's basically there's like a whole thing with how the logic gates sort of like work.
It just sounds so obscure. Like if you're using electrons,
Yeah.
it's like on a quantum level. I don't know how you'd like build a gate to stop. I guess that's what you were talking about earlier with the electrons messing up or quantum tunneling and stuff.
Yeah. So basically, when I googled it, most of them are like expressed in the form of like mathematical operations, which most logic gates can be expressed as. But I actually don't know how they implement it like in a physical reality.
It's probably proprietary.
Yeah.
Yeah, like quantum computers are huge, and that's probably mostly because of the cooling system.
Yeah.
But I wonder how. I've never like actually seen what it looks like the actual thing. Quantum computing.
So one of the implementations of quantum computing that's like not electron based uses like the polarization of a photon. So a photon, I think, is either like right polarized or left polarized, and it's similar in that it's like in superposition. So that sort of can be measured. It's like photons bouncing around, and I assume they use like mirrors and stuff. But yeah, so that's one way to do it. I don't know how they do it with electrons, but with photons, I
That's
think it's
really cool.
just yeah.
I didn't know electrons or photons had a.
Yeah, so there's different types of like you can technically make like you can make a lot of objects into qubits, right? As long as they have this property of like they can be put into superposition.
Mhm.
So photons are one, electrons are another. Even entire nucleuses and like their magnetic resonance moment, I think, can be used as like a qubit. So yeah.
What companies are working on quantum computers? Google, IBM, any?
As far as I know, Google and IBM are like the big ones. I think DARPA might be working on one, but
Google has like Bristlecone, right?
yeah, BristleCon. That's what they're October 2019. Um,
Is NASA
IBM.
working on it? I don't know.
Apparently, Intel's working on one.
Interesting.
Uh, Honeywell, Lockheed Martin,
Wait, can you
Microsoft
can you
Research.
explain how it what you meant by its application to nuclear fusion?
Yeah, or so the parallel. Um,
Parallel
so nuclear fusion and quantum computing have both been like these technologies that have been sort of touted since or like hyped
Yeah,
up since the 1960s.
yeah,
Um, they both have these like sort of devil in the details problems. Nuclear fusion, for example, right? You have this giant hot like 150 million Kelvin plasma,
right.
and you have to somehow confine it, and you somehow have to control it, and you somehow have to extract energy from it. And so that actually also requires a huge amount of cooling. You have to cool your magnets using cryogenic helium.
Okay.
And there's also like a bunch of like instabilities, right? So it's a very difficult problem.
Yeah,
And it's a sort of similar thing with quantum computing. It's a very difficult problem. There's a lot of like superconducting technology, a lot of cooling technology, a lot of trying to avoid noise. And so both fusion and quantum computing have like their share of pretty smart skeptics who say, okay, we've been trying to pursue these for 50, 60 years, and we haven't seen anything yet because it's just so difficult. So it's just sort of an interesting parallel in that they both have like a huge amount of promise, but also it's so difficult and there's so many details that are killing the thing. So
right.
anything else or
Do you know what D-wave systems are? Did you? I think you talked about that a little bit.
yeah, so D-Wave, I would like a lot of their stuff is proprietary, so it's hard to figure out like exactly what's going on. But for example, they claim to achieve like a 300 million times speed up in some algorithm, right?
Oh,
But it turns out that this speed up could be just as easily implemented on a classical computer. It wasn't actually because they're like quantum computing. It was because they used a more efficient algorithm. So
okay.
D-Wave, there's a lot of shady stuff going on as essentially like, are these people actually doing quantum computing or are they just like
Yeah,
throwing around buzzwords so they can get more investment capital and more
right.
media hype? So yeah.
Cool. It's really interesting.
And I think this would also affect Active Directory, which I think uses RSA. I'm not sure, but it's somewhere in the range of a few thousand bit encryption. So again, every company that uses Windows and I'm just saying Active Directory, but this could be applied to anything else. So yeah. Everything's open source.
And in terms of there's a few other things that are interesting that I didn't put in. So there's a few companies, like I think TensorFlow has this like quantum machine learning library, which basically, and I think they have like a way to simulate a quantum computer on your computer or on some server or something. Because yeah, quantum computers, they can be simulated on like a classical computer. It just takes a huge amount of resources. It's horribly inefficient. But yeah, there are like a few quantum libraries I know in Python, so that could be interesting to play around with. I haven't played around with them myself, but it could be interesting.
I'm reading about quantum computing or quantum tunneling. Even though like you mentioned like some bad things that can happen when you use it, or like some bad effects from quantum tunneling when you have quantum computing, but they also talk about like the junctions from the current.
The PN junctions?
Huh?
The PN junctions?
The Josephson junction. It's like an electrical element that doesn't exist in normal conductors. I don't know exactly what the application of it is, but I feel like quantum tunneling can be useful somehow with quantum computing.
Oh, that's I just googled it. Apparently, it's used in like superconductors.
Yeah.
That's cool. Yeah, so it's not like quantum tunneling is necessarily a bad thing, but in like current CPU designs, quantum tunneling is to be avoided because it's. But yeah, like actually, life wouldn't be able to exist without quantum tunneling because without quantum tunneling, fusion in the sun wouldn't be occurring enough, so our Earth would be like a lifeless cold hulk. So
I should read more about that. Sounds really
yeah.
interesting.
Yeah, quantum stuff is extremely interesting. I mean,